Hi, this project is on the topic of conventions and multi-agent collaboration. To do well in a team sport, you have to be good at the skills fundamental to the game. For example, in basketball, you have to know how to shoot the ball well. But perhaps more importantly, you have to know how to coordinate with your teammates. That's why teammates practice together instead of separately, so they can develop shared understanding of the team strategy. For example, here, who is the setter going to set the ball for? We may not know, but they certainly do. There is some shared understanding that these teammates have developed through practice. Or say you're in the countryside and there's an oncoming car. Which side of the road do you keep to? Well, if you're in North America, there's a convention to keep to your right. So clearly, multi-agent collaboration requires knowing two things. First, how to be good at the task, and second, how to coordinate with your partners. So more concretely, here's a task where two people try to reconstruct the grid, with player one, the boy, controlling the red block, and player two, the girl, controlling the blue block. At the beginning, player one can see the goal grid, but player two cannot, and they start off with an empty grid. So player one might start placing the red block on the top right, and player two might do nothing. Player one might move the red block to the bottom right, and player two might move the blue block to the top left, based on conventions that they've developed and from the signals of the past few moves. So from player one's perspective, there's two components to solving this task. First, placing the red block correctly, and second, signaling the location of the blue block to his partner. So going back to our earlier slide, multi-agent collaboration requires knowing two things, and going forward, we'll refer to these two things as rules and conventions. A common definition of conventions is a shared representation that breaks symmetry between equally optimal strategies that can be developed over repeated interactions. So in this project, we want to learn separate representations for conventions and rules to better adapt to new situations, whether it be new tasks or new partners. So there are two axes of generalization at play. First, when we have a new partner and a fixed task. For example, we might want to play with grandpa now on the same task. So since the task hasn't changed, we'll reuse the same rule representation, but now we'll learn a new convention representation. Or we might want to play a new task with the same partner. So here, since the partner is the same, we'll reuse the same convention representation, but we'll try to learn a new rule representation since the task has slightly shifted. So to do so in our project, we use a modular architecture to work with new combinations of partners and tasks. Here's how our framework works. So we take in a state observation S into the task module, which outputs an action distribution. You can think of this as what action would you take if you don't know the identity of your partner. Then we have a partner module, which outputs a separate action distribution, which roughly corresponds to the conventions that partners have developed. And we simply compose these two action distributions by multiplying them together. And for each partner, we have a separate partner module that outputs a different action distribution. So with this modular architecture, we're able to swap out partners and task modules when we're adapting to new situations with new partners and new tasks. We have a regularization term to make sure that the task and partner modules are learning the correct representations. We experiment on a variety of different tasks, including collaborative multi-arm bandit, block placing task, and Hanabi. For each task, we fix the rule of the game, play with a few training partners, and try to adapt to a new partner at test time. In gray, we show some common fine-tuning and meta-learning baselines, and we show that our method in orange is able to adapt more quickly to a new partner. Similarly for the block and Hanabi game. Next, we also look at adapting to a new task, where now we're fixing the partner and the conventions that our partner is using, but tweaking the rule of the game a little. And again, we show that our method is able to coordinate better on this new task compared to common fine-tuning methods. So in summary, collaborative tasks involve a combination of rule and conventions. The same rules may carry over to different partners, the same conventions may carry over to different tasks. And we show that learning separate, composable representations for rules and conventions allows us to quickly adapt to new settings, whether it be new tasks or new partners.